This detailed analysis deconstructs the mathematical and physical behavior of a purely capacitive circuit operating under alternating current. This diagram shows the setup: a single capacitor connected to an AC voltage source defined by V equals V sub m sine omega t. Applying Kirchhoff's voltage law, the voltage drop across the capacitor equals the instantaneous voltage supplied by the source. Expressing this in terms of charge, since Q equals capacitance times voltage, the charge perfectly tracks the source voltage. Because the driving voltage is a sine wave, the charge accumulating on the capacitor's plates also oscillates as a perfect sine wave. This continuous oscillation of charge creates a specific type of current flow, one that follows different physical constraints than a simple DC circuit. To find the current, we look at the rate of change of charge over time, expressed here by the derivative dq dt. Differentiating our charge equation brings the angular frequency, omega, to the front and transforms the sine function into a cosine function. Mathematically, this derivative operation confirms that the current waveform follows a cosine path. Using trigonometric identities, we can rewrite this cosine wave as a sine wave that has been shifted forward by 90 degrees, or pi over 2 radians. This finalized equation for current, shown here in the top box, includes that positive pi over 2 phase constant. This shift indicates that the peak current occurs a full quarter cycle before the voltage reaches its own peak. In a pure capacitor, the current leads the voltage, creating a permanent offset between the two signals. If we isolate the current amplitude, I sub m, we can rearrange the variables to resemble Ohm's law, where current equals voltage divided by a resistance-like term. This term, 1 over omega c, is capacitive reactance. It represents the opposition a capacitor offers to alternating current and is measured in ohms. The value of this reactance depends on the angular frequency, omega, which measures how fast the current alternates. These graphs plot the inverse relationship between frequency and reactance. As the frequency of the AC source increases, the capacitive reactance decreases, allowing current to pass more easily. At a frequency of 0, which is direct current, the reactance becomes infinite. Because of this infinite reactance, a capacitor blocks the flow of steady DC once it has reached full charge. Capacitors function as frequency-dependent resistors, acting as an open circuit for DC while providing a path for high-frequency AC signals. To visualize the relationship between these magnitudes and their phase shift, we use a phasor diagram. These two vectors represent peak voltage and current, locked at a 90-degree angle to represent the phase lead of the current. In an active AC circuit, these vectors rotate counterclockwise at a constant angular velocity. The current vector always maintains its lead over the voltage vector. The instantaneous voltage and current values are found by taking the vertical projections of these spinning arrows onto the y-axis. Mapping these y-axis values over time generates the sine and cosine waves we see in the time domain graph. On the graph, the blue current wave reaches its maximum exactly 1/4 of the cycle before the green voltage wave does. The mathematical derivation and the visual plot both show that voltage and current are out of sync, which changes how the circuit handles power. With the current and voltage peaks offset, we have to calculate how much energy is actually being used. Instantaneous power, P, is the product of the voltage and current at any specific moment. We multiply our sine-based voltage equation by our shifted current equation. Simplification through trigonometric identities results in the power equation shown in the box. In this result, the angular frequency is 2 omega t. This means the power cycle oscillates at twice the frequency of the source voltage. Overlapping the power wave with our original V and I signals shows that the power reaches 0 every time either the voltage or current crosses the axis. During the positive portion of the power wave, the capacitor draws energy to build up its internal electric field. When the source voltage drops, the capacitor discharges and returns that stored energy to the source. Because of the 90-degree phase shift, the energy absorbed is exactly equal to the energy returned over each cycle. The mathematical conclusion, shown in the bottom box, is that the average power consumed over a full cycle is 0. Even though the alternating current flows continuously back and forth, there is absolutely no net energy loss in a pure capacitive circuit. A pure capacitor acts as a frictionless energy spring, borrowing and returning energy in a continuous cycle throughout the alternating current landscape.